Well, thanks, Dave. Thanks for inviting me here. It's great. I went to grad school up here in Seattle at UW, so I always love coming back to the Pacific Northwest, especially where the weather is nice as it's been the last few days, and I'm sure it's not going to be that way all winters. It's just like it is in California, right? But today, I'd like to talk to you a little bit about what David asked me to talk about is about non-traditional careers. And so I thought I'd, now that I've just retired from my full-time job anyway, from the Monterey Bay Aquarium Research Institute down in Monterey, I thought I'd talk a little bit about both what I did as a chemical oceanographer, how I got into it, and then at the end, more for the students probably, talk a little bit about what I learned along the way and what helped me out along the way in order to have the career I did. So with that, I'd like to talk a little bit about non-traditional careers. If you look at universities, a lot of universities tend to really put people in boxes, and you tend to have people in science or in engineering, and that works well for some people, but I think in today's world, a lot of the students I see, as well as our own kids, it's those kind of traditional jobs are harder and harder to find, and students have to become more creative in creating careers these days, and I think RAIN is right in there with that, as well as many other programs. But since I was always trying to balance between chemistry and engineering, one of the things I think David wanted me to come up here and talk about that a little bit. So let's see, to give you a little bit of an overview of my job, I want you to have keep a couple things in mind. One of it is, why did I call the talk Brains and Thumbs and Probability and Possibility? And right now, I'm not going to tell you. I want you to keep that thought in mind a little bit, and hopefully it'll become clear as I go through the talk. The other theme that I want you to think about is tool belts. And I like to call it tool belts because I think all of us have our certain abilities and capabilities and things we learned. And if you look at those as tools, as you go through life, you slowly fill up your tool belt with different kinds of tools. And I think the important thing is that really tool belts are different for everybody. And that's a good thing, because we want to have a good diversity out there. And in order to sell yourself, the more unique you are, often the better you are. And so in that sense, tool belts are really, the tools in your tool belt should be different for everybody, and but they should also be things that really interest you. What you want to do is really have tools in your tool belt that drive your interest, because that'll be what you'll be most efficient at, and what everybody really is efficient about that. So keep those two things in mind, and we'll come back to them. Okay, so first of all, when I was young, I grew up, as David said, in a little town in Woods Hole. There wasn't a lot to do over there. A lot of us used to go, as little boys, go biking, and we really enjoyed kind of developing bikes, and with friends we'd build bikes. Back then it was mostly still old 3 speeds. We'd actually figure out, this was before mountain bikes, and just as early 10 speeds came in, we used to put roofing nails through the larger tires, clip them off, put a smaller tire inside of it, inflate it up to 80 PSI, and those were kind of our mud tires, how we'd ride through the woods over there. Of course, when you ride a lot of bikes, bikes also break. So back in those days, we had a lot of 3-speed hubs, and so when a 3-speed hub breaks, you throw it away? No, we as kids didn't have the money to replace them or to fix them, so we learned how to fix them ourselves. And I think I'm telling you this because this is really part of where your interests and your tools start. So we started taking apart 3-speed hubs, learned how they do it, and it's really not that difficult. You can do it, and we learned it, and we played around quite a bit with that. So there's one thing that I really learned there is I like to tinker, and that's one of the things that I learned early on. So from there, I went back to, you like biking, I had basically two things I did. I washed a lot of glassware on Woods Hole. The only places you can really get jobs is at the Oceanographic Institution, washing glassware, or at the gas station pumping gas. I didn't really want to breathe gas fumes all day. So I was started washing glassware, and really got interested basically from two things. One was I worked in a chemistry lab, got my first interest in chemistry going there, and we also had a really good chemistry teacher in high school. It's always these single teachers that you seem to create a lot of excitement in you, that get your interest up. So it was a good chemistry teacher and working in chemistry labs that got me off to college studying chemistry. I was also good in math, and thought I was going to be a math major at first, but that didn't last long. After my first math test, I was pretty quick switching out of there. But I did enjoy chemistry, and and because I enjoyed tinkering, I spent a fair bit of time also, instead of taking physics courses, taking basic engineering courses, and got a waiver there to be able to do all my physics requirements in engineering. So that was, I did learn quite a bit there. One of the things, after college, I graduated from college and with a degree in chemistry, and then went back to the Oceanographic Institution at first. I had continued kind of my summer job as a full-time job. I worked more in studying marine sediments, where looking at particle fluxes down through the ocean water column, looking at the composition of those sediments, looking at overall fluxes of both carbon as well as various other organic compounds from dying plankton that settle out in the ocean or that are decomposed by bacteria down deeper. So you look at fluxes up high and then look at down deeper and seeing how fast they decompose. Normally, if you look at an ocean water column, there's a lot of particles, and then less and less and less, they get finer and finer as they decompose, and that actually matches up very well with oxygen being consumed. So you can see down deep at about 700 meters deep, you'll see an oxygen minimum, which is also which correlates with the maximum reduction in the particle size or the consumption of all of the organic particles that go down in the water column. So while I was working there, I started developing some sediment traps that we used, a new kind of sediment trap, a sequential sediment trap you have a series of cups underneath a big funnel. Back in those days, before a lot of CAD stuff, we figured out how to build these, how to design out of a flat sheet of plastic, how to design a funnel that was eccentrically in a big tube that went down and collected particles above one container, where we had a whole disc of containers that rotated underneath the funnel so we could do a time series. Those sediment traps worked pretty well. I ended up having the opportunity to go on a research cruise to the Eastern Mediterranean and deploy them out there, and so I got my first interest in travel and working out at sea, and that was quite enjoyable, and that hooked me a little bit more even on oceanography. So I got back from that cruise and had, like most people, had an old car that had been sitting for a while that wasn't running very smoothly. So I had to figure out what to do with that old VW, and voila, I had nightmares about the car. But luckily, there was a great book called Poor Richard's Rabbit Book that very well explained, at least well to me, on how to rebuild an engine. And it basically, if you have the nightmare with all the car parts, you can think about how to build a sandwich like that. You can take an engine apart and put it back together again. And you just you do these things. It took me, I was 22 years old, and it basically took me about 2 weeks to go take that engine all apart, every single ring, every single piston, put new rings in it, got it all figured out, put it all back together again. And when you put a little gas in the carburetor and the first time you turn that key and the engine starts and purrs, it's a pretty darn good feeling. So again, it's when you learn tools for your tool belt, it's really good to do things as well. Anyway, after I got back from that cruise and I was looking for further jobs, I got two really good opportunities. One was because I had been on that German research vessel. I met a bunch of Germans there who were from the Technical University of Germany, and I was able to work over in Germany for a year and over in Munich and design the same kind of sediment traps I did, but over with a few additional features, and work over there in the sedimentology department, and we deployed these throughout lakes in Germany, in Chiemsee, south of Munich, and then in Lake Constance down with a bunch of Swiss people, and had a great time. The second opportunity was when I was doing all our bike work, I actually started a little bike shop summers as well. Had a little bike shop that I ran, fixing bikes for people. Woods Hole's a small town, especially in the summer. A lot of people bike around because traffic doesn't move at all. And it's kind of like I-5 except on one-lane roads. And I ended up running this little bike shop for people. And one of the people that came by, I had washed glassware for years before, and I asked her what she was doing. She said, oh, she was working down in the Antarctic. And to me, boy, I couldn't get that thought out of my head, like, Antarctic, that would be so cool. So I ended up writing her a letter and saying, boy, if she need anybody in the Antarctic, I'd do anything to get down there. I didn't hear from her for about 6 or 8 months, and then all of a sudden my boss, Woods Hole, started asking me, who's this person, Audrey Haschemeyer, keeps asking about you. And I didn't think anything at the beginning, and then all of a sudden she called me up and said, I'd like to go to the Antarctic. 6 weeks, be at Point Magoo on the West Coast, and we dropped everything. I talked to my good friend, asked him whether he could bring me to the airport, and he said, sure. And I said, we're sitting at a bar, you've already had a couple of beers. You don't know which airport. And I told him, LAX. This was from the East Coast, so he says, okay, I'll call you in the morning. He called me at 7 o'clock in the morning. All right, I just quit my job at the boatyard, let's go. So a week later, we were on the road, drove cross country, went to Point Magoo, and off started a wonderful, basically for 3 years, I worked at actually Hunter College in New York City, but on the Antarctic research program. We went down actually on an amazing, our 125-foot wooden boat. It was the last of National Science Foundation's wooden boats, double-hulled boat for ice duty that went down, across the Great Passage. Everybody was not sampling, we were reverse sampling, if anything. And we went down, and the instant we got in the ice, everything got quite a bit calmer, and we passed these beautiful icebergs and worked at a station. This is Palmer Station, south of South America. And this is about a little below the Antarctic Circle. And that's basically, you're in the middle of rocks and glaciers, and the boat is moored right on in front of a little dock. And those buildings, I spent a total of 13 months on the ice, twice for 5 months and once for 3 months. So this is Palmer Station. I also worked at McMurdo on the other side of the island. But we were working on a project. The woman I was working for, who I had washed glassware before, those little trematomas fish up on the upper right, they're pretty ugly. But the cool thing is, these fish live in water that is colder than the freezing point of their blood. Most animals down there, like sponges and so forth, have 3.5% salt in their blood, just like seawater. But humans and more advanced animals, like these fish, I'm not saying we're like those fish, but we only have less than just about 1% salt in our blood, and they we worked on how they do this, how they were able to supercool their blood. And that ended up being, that's a whole neat story, how they have this antifreeze glycoprotein that wraps itself around nucleating particles before they reach the critical size and can grow naturally. So they, by these proteins wrapping themselves tightly around nucleating particles, they'll naturally dissolve again. And if you take just a tiny piece of ice in a syringe and inject that in their veins, that will then, is larger than the critical size. That'll grow slowly throughout the veins until the whole fish freezes. And we wrote that paper, gosh, in 1981 or 82, and that still stands today. So it's, you know, that was a lot of fun work. So anyway, with all that, I really enjoyed traveling and enjoyed oceanography, and went on from there to go to grad school. Decided finally to go to grad school, but going to grad school now after a kind of a 4-year gap, for me was a really good thing, and I recommend that. I've had a lot of students now, and I really recommend that because it's a time where you can really develop your interests, know what you want to do. So as I went to grad school here in Seattle and Washington, I knew a lot more what I wanted to do, what my goals were, and that really helped a lot. So I went up here to Seattle, loved Seattle, loved hiking and climbing and everything, but ended up studying trace metals in the Eastern Equatorial Pacific, and we did quite a bit of work, had a couple months, cruises, we had cruises all over. I probably spent 9 months at sea during grad school, but the big cruise that I did for my thesis was out of Panama and around the Galapagos Islands, looking at taking samples of water for trace metals all around the Galapagos Islands in the Eastern Equatorial Pacific. So that was, ended up doing quite a bit of work there, and finally graduating with a big thesis where I think the biggest thing I realized afterwards is how little I could say from all the samples I collected, how little I could really say what was happening. I could describe what we observed, I could do that, but the whole goal of trying to look what happens as the equatorial countercurrent comes across and all the metals are upwelled around there, how they behave. I could describe what was there, but I couldn't really say enough to say about what was really happening, which was kind of my initial goal. So I kind of left grad school saying, boy, I really have to figure out a way that we can get kind of an order of magnitude more data. It was also the same time that satellites were now collecting more oceanographic data, and we were realizing that the ocean is a much more dynamic place than you normally think of it. When you take samples here and there you can take them quite deep, take various samples, but your stations are quite far apart. You have to have a lot of assumptions that you have. Trace metal concentration is one over here and another over here. You kind of have to assume that it evenly goes in between the two. You have to interpret between the two, and that turns out to be kind of really not a very good assumption. The other is that over time, things change drastically. And that's one thing that's real hard to do when you're only sampling. In fact, you only sample out in the ocean generally when the weather is good. When the weather's bad, the decks are closed, it's too dangerous to be out there. So we were getting a very biased view of the ocean in many ways, because when the ocean is highly dynamic, during storms, that's when things happen, not when everything is nice and calm and you're out there collecting samples and data. So basically what I'll describe now is kind of after that, I had a great opportunity to go to a brand new research institute at the time called the Monterey Bay Aquarium Research Institute. It was funded by David Packard. He had also funded the initial building of the Monterey Bay Aquarium that his daughter Julie Packard runs, and David Packard, who at the time was sitting at about $12 billion, and was trying to figure out what to do with them. He ended up losing quite a bit of money, and the stock market crashed because most of the stock was HP and went from 12 in 2003, went from 12.8, I think, to 3.5 billion dollars. So that was losing a lot. But still, he wanted to figure out what he could do. He realized he couldn't do a lot of big dent in medicine, but he did want to kind of work a little bit with his daughter, who was really interested in the ocean and preserving the ocean. And so they started the Monterey Bay Aquarium Research Institute in 1987, just a couple of years before I got there. And really to look at the deep ocean, because David Packard really felt like, as often said, we know less about the bottom of the ocean than we know about the backside of the moon. And that was really true. So we became an institution where the idea is that we would get remotely operated vehicles and we would study the deep ocean. The one other thing David Packard brought to that institute was an idea that really rang with my idea of trying to balance engineering and science, is that he felt to make the biggest steps in science, you can't just use the traditional approach of scientists asking the questions, figuring out what needs to be done, and then having engineers go and build whatever instruments that you need to test your hypothesis. So he felt the best way to do that is to bring scientists and engineers together from the same level. That you have senior scientists and senior engineers working together to basically come up with projects that have reasonable scientific questions that you can answer with instruments that you can develop and build. It's very easy to ask scientific questions that can't be answered. You know, people put forward hypotheses like Gaia. They're great hypotheses, but you never can prove them. And so if you can, the best scientific questions that make the best advances in science are the ones that are supported by engineering developments that are reasonable and scientific questions that are reasonable. So that's why why David Packard wanted to put scientists and engineers on the same level, and all successful projects have a main engineer and a main scientist on it, and that was the idea behind MBARI. We had a couple of growth years, you know, trying to figure things out, but overall, that's worked really well, and to me, that sounded really good, and I was the first director of the Institute came up to UW to give a talk, and rumor had it that whoever asked him for a job didn't get one, so we were a couple of grad students kind of took him out to lunch and really never said anything until he offered us a postdoc, and we were there. So that was the beginning of the rest of my career, it turned out. So once I was there, I worked mostly on developing chemical sensors for in situ chemical sensors, which is what I really wanted to do. I headed up a chemical sensor program for a number of years, and we developed Osmo analyzers, which were osmotically pumped chemical analyzers that could run for a long period of time, or use an osmotic pump, basically a salt gradient across a permeable gradient through where water could diffuse through the membrane but not salt. So you can have basically, rather than a battery driving the pump, the battery becomes a osmotic membrane with salt on one side, distilled water on the other side, drives, or Brownian motion through diffusion drives water, and you have a net flow from the freshwater side trying to dilute out the saltwater side, and those you can make very stable, make them pump. They do pump as a function of temperature, and so you have to account for that, but we made little chemical analyzers that pulled in sample, added reagents, made usually a color or something that we'd observed. So we built sensors for all sorts of nutrients and even some trace metals. We ended up deploying them all in the upper ocean. We had definitely, with temperature variability, we had a little bit of an issue. They ended up being really useful at the bottom of the ocean where temperature doesn't change, and we monitored hydrothermal vents and and certain metal concentrations down there, and that worked out really well. And I'll talk a little bit about that. And then we also then looked at chemical monitoring, and I adapted the osmotic pump basically to look at, to pull sample in and monitor, and I'll talk a little bit about that. As an instrument we call Osmo samplers, and we looked at that quite a bit to look at the role of the ocean in plate tectonics. So we studied fluid flow both at the bottom of the ocean as well as down in the crust, and I'll talk more about that. And my most recent thing that we've been working on is high precision pH, looking at the role of climate change and CO2 intrusion into the ocean from the atmosphere, from anthropogenic sources, and looking at really trying to quantify the role, how much CO2 goes in the ocean and ocean acidification by these high precision pH sensors. And I'll talk more about that. So first of all, these are a couple of the sensors we developed. On the left here, this happens to be on a float head, but on that left stem is one of the high precision pH sensors. Also shown on the right, it's a little silicon chip that actually is 9 selective electrode, and we can basically refine that over time, and we can now, rather than a regular pH electrode that if you played with them, they're good plus or minus 0.1 or maybe 0.05, and you got to calibrate them about 3 times a day. Our goal here is to put these in the ocean, leave them there, and measure pH down to 0.002 for stable for 5 years, so we can go out there. And we're probably down to 0.003 right now or so, but still got a little bit to go. But overall, those are the kind of sensors we developed. The one on the right is an optical probe. It is a probe for nitrate. We actually, inside the float, we have a UV light source and a little Zeiss spectrophotometer, and we can look at nitrate absorption in seawater. That's actually done by, there's a big bromine absorption, so you're looking at the edge of a big bromine peak, which is proportional salinity. We're looking at a few nitrate peaks, and we can, turns out, quite precisely monitor nitrate that way. And again, we can do that with fairly low power. When we develop these sensors, we often go out to we have a couple local test bed moorings. The Lobo mooring on the left, I designed that mooring. We have it out in Elkhorn Slough behind us, and occasionally out in Monterey Bay as well, a similar mooring, loaded with all sorts of battery packs on the outside and optical meters, CTDs, which measure conductivity, temperature, and depth. And then we have another instrument cage down about 3 meters deep, so we can see what's different at the surface and down deep. And this is anchored with a railroad wheel, big heavy railroad wheel at the bottom. We have these we leave them out for about 18 months. Here we do have to clean them periodically, and on the bottom center is what the moorings look like when they're just in Elkhorn Slough, and up on the right is when we get them back and have to clean them. They'll sometimes look like that. Yes?
How often do you have the measurements being taken?
So here we normally, we take measurements once an hour. So all the instruments take a measurement every hour. Actually, a lot of the instruments are in a pumped flow stream, so we can actually pump fresh seawater past all of them. And then we take hourly samples. Hourly samples are collected by a central recorder, radioed up on top of the mooring. What you see on the top there is a radio housing. We have basically, back when we started these, there wasn't any cellular connectivity out in Elkhorn Slough, so we set up an Ethernet backbone, wireless Ethernet backbone to a shore station and recorded. And we had up to 5 of these moorings in the bay at a time, studying all the at various locations, looking at nitrate running off from we did published all sorts of papers on the data from nitrate coming off the strawberry fields to the salinity when it rained versus not raining areas, what happened. And so it was, we got quite a few papers out of them. We had these There's still one mooring of these that's still going. You can actually look up MBARI logo data, and one of the things we do at MBARI too is this data is collected, and when it's collected within 1 hour, it is on the web available to anybody. And at least in a raw state, within a month, we try and data process it and get it quality controlled so that it's usable by everybody. But that's another thing that we really try and do is get the data out there. So there's high school programs that use some of this data. There's college programs as a whole. We actually have an education research specialist who works on with schools and so forth to get schools to utilize the data and be able to use it for educational programs. But scientists use it as well, and we try and not hold on the data for too long so that people can use it for all sorts of a government policy as well as for publishing, scientific publishing, and we just have to be one of the many people also working with that data. It is very interesting when we get these back sometimes, and there can be quite a bit fouling. Biofouling is a huge problem in oceanography, especially when things are sitting up in the ocean, and there's quite a number of ways we deal it. Still, the best is that screen there that's totally clean where the samplers underneath it is copper, and copper is still one of the best anti-foulants around, or various copper nickel alloys that exist. But when you get gooseneck, barnacles, and other animals coming through, it's incredible what they can do, and our moorings can be quite heavy at a time. But, so this is where we test these out locally, and then we've taken a lot of our sensors and gone around the world and deployed them on various with larger oceanographic programs. Often we put them on these larger moorings that on the left that were also developed at MBARI. We have them in Monterey Bay, but they're also out at 2 major time series stations that have been used by the National Science Foundation for doing oceanographic work. One is north of Hawaii, north of Oahu. That's Oahu right here, and then the mooring is up in the middle of the, it's about 60 miles north of Oahu. It's a deep ocean station, so it really isn't that influenced by land. There's another one called BATS, Bermuda Atlantic Time Series, that's off of Bermuda, so we don't have coastal effects, and it's a great place to make it somewhat easily to get to and yet be able to be not a total local phenomenon. These are, we can really look at open ocean processes out there. So these moorings are there. This one is down is more than 6,000 meters of water. So we have instruments up and down through there. For nitrate, we mostly, and pH, we've only measured mostly in the upper water column on here, but we mount these sensors and leave them out there for anywhere between 18 and 24 months when they need replacement. The mooring does get replaced every 18 months, but which if you look at a long-term time record, in this case of pH in Hawaii, you can, where the gaps are where the mooring was replaced, but overall we can really see the ocean acidification that's taken place over the years from 1988 out to 2010. And so you can, ocean acidification definitely is real. So anyway, we've deployed these quite a bit, and sensors. And then this is also the osmotic sampler that I talked about, that we use to study the role of the ocean in plate tectonics. This is where you have water you think of water being on top of the seafloor, but water goes quite down deep through the sediments and also into the rock, into the lithosphere, through the rock. The denser it is, the slower water flows, but it is all permeable and does flow through there. So often, there was a great interest in these. We developed these at MBARI. They're basically the ultimate of kind of KISS instruments, keep it simple, With the osmotic membranes up top, you see the little white sheaths in the top, and we have salt. We have salt around them in the bottom, normally not shown here in this bottom compartment, and then fresh water in the top. You have a net flow going up, and then you have a long coil of like less than 1 millimeter diameter, inside diameter tubing. That sample gets drawn through anywhere from 2 to 20 mils per week. But that's enough. From 1 mil, we can do ICP-MS sample on, and various other methods. We can get about 40 to plus elements out of there. So rather than studying one element, we can now do 40 elements. Because of the slow flow in a tube, you actually get really good plug flow because you get radial diffusion that keeps your sample from smearing along. And on many very deep cores where we have up to some of the longest deployments where we're over 4 years at the seafloor, you can pull sample through over 2 kilometers worth of tubing, and we still get peak smearing going from pure. The tube is initially filled with fresh water, so the pump only fills at the bottom with fresh water. That the salt water to freshwater interface is still less than a couple of meters. It's pretty incredible how good you have blood flow. So when we get these samplers back, we take that long tubing, we cut it up into about 1 meter sections, about 1 mil, put it in little microcentrifuge vials, and we can analyze them as time series. We won't analyze them all to begin with. We might do every 10th one, because often things are the same, but when there's seismic activities in the area or anything like that, that's when we do a finer sampling and look for what happens during that time. And you can see quite a bit of changes. So when there's a seismic activity, the fluid, often what we see first is increased silica, and silica we believe actually already before a seismic event, silica is released very rapidly as rock undergoes strain, and because it's given off when microcracks form, silica dissolves quite rapidly, and we hope that this may at some point be an early detection mechanism for earthquakes and things like that. So that's kind of one of the reasons that this work is done. Often we have on the samplers on the seafloor, you see on the upper right, a lot of animals love them, and we use them there. We've also, when I use these samplers down deep in boreholes, so this is when we look at down deep in faults or in subduction zones or other areas. There, we put a lot of these holes we can drill up to, where the Joides Resolution is the American drill ship that is part of this program. It's quite a large ship and has about a crew of about 114 people, operates 24 hours a day, will go out for 2 months at a time. It's about $6 million for a 2-month cruise, and they will drill in a certain part of the ocean that's been predetermined, and then a lot of scientists come together to be able to try and use these samples. So there's geophysicists, geologists, all sorts of people. They drill a hole, bring back a lot of rock samples and so forth. But what our interest is, when after the holes are drilled, we can then install instruments that then monitor that hole over a long period of time. And that's where I've been involved in doing the water sampling. And on the upper left here, you can see we're putting all these sample coils, pumps, and everything together. There can be quite long instruments. They're then brought to the drill floor, bolted in line in a string that goes down the borehole. The very last thing to do is then a little plug on top that plugs that hole, and we'll leave it there for anywhere from 1 to 5 years, and then we go back, bring it up, and bring the samplers back on deck and begin analyzing them. Usually we turn the sample around, so we put another sampler down there as well. it's quite an operation to see, and it takes a lot of preparation for, but it's a pretty interesting capability, and is definitely, when you're out for 2 months at sea, it's quite an interesting process watching that all work. When they go down, they have to put miles and miles of pipe together to go drill, and I think I have a picture later of that, but they have to bolt each one of these individual pipe sections about 30 meters at a time. They screw the pipe together and lower it down, all the way down with a drill bit. They drill, then pump water down in the borehole, and then flushes this out, and they can actually drill holes over 1,000 meters deep in through sediment, and then through 1,000 meters of bedrock. And we've learned quite a lot about the water down there since then. One of the places we've gone is in the subduction zone off of Costa Rica, where we study the water that's in the sediment, and because this is a unique place where most of the sediments that come off the Pacific plate on the left, coming on the left, riding underneath the North American plate on the right, most of the sediments are subducted. And we had 2 boreholes, one on the left side in the sediments, where we looked at kind of fluid composition and fluid flow before the sediment is subducted. And then on the right, we drilled, you see the little yellow line on the right through that the middle blue arrow. That was our other hole, and we went down about 800 meters of rock, and then into what's called the décollement, is that upper area right below where the sediment slides down and the rock over North American plate overrides it. And that's where a lot of, as the sediments are compressed, water slowly flows back up out of there. And we were looking at the composition of the water that goes out, so we could learn a little bit, okay, which elements are coming back out of the pore water that were there to begin with from the left hole, and which ones are being subducted. And knowing that is a big part of looking at all the elemental cycles in the ocean, because this is one of the biggest unknowns of how many metals or ions leave the ocean that way versus how many are pushed back in, are really squeezed back in the ocean. So it's a function of solubility and reaction with the sediments. This is important also because all these sediments are subducted, and all these back arc volcanoes, much like Mount St. Helens and all the volcanoes over here, is these sediments get subducted and will then come back up in plutons in these back arc volcanoes. And the reason they're so explosive here versus like Hawaii is all the water that's in that magma, and that all that water comes from these areas being subducted. We weren't necessarily studying the water, but we were looking at the elements that are in there. And again, there was other people who are very interested, the volcanologists, in this data, because they're looking at what's being subducted in terms of elements, in terms of what goes into the magma. Initially, we drilled them and put the instruments down, but when we replace them, the drill ship is too expensive, so we go down in Alvin. And Alvin is, for those of you who've never heard of Alvin, is the submersible that actually found the Titanic. It's probably her most famous expedition, but she is a 6-foot diameter titanium sphere and is in Woods Hole. And so when you get in there, it's not like scuba diving. You're in one atmosphere in that titanium sphere. You go down, and just when they leave the surface, they're still lit up here. You can see what Alvin looks like with her tool sled up front. Inside the 6-foot diameter sphere, there's 3 people, 2 observers, 2 science observers, and a pilot. It gets pretty cozy in there. And so you're in there in this picture with my son, Nico. He gave me his Lamy to take. It was actually not totally legal because you're not supposed to take anything plastic down there, because if there's a fire in there, it's the toxins from the plastic that'll be pretty bad for you. But right behind my head is also the lithium hydroxide canister that absorbs all the CO2, because they have oxygen tanks, slowly bleed oxygen in there. but the lithium hydroxide sucks out the CO2. And so that's what it looks like inside Alvin. You're pretty cramped in there. You can be on a long dive. You can be up to 13 hours down there. So sitting there with your legs piled on top of each other. So it's an interesting experience, but it's really, we dove down, right down the trough there is 4,300 meters. So that's the deepest I've been, is 4,300 meters. And it's pretty cool going down there. Actually, one of my side effects is that junction there is actually, we traveled a ways from that left borehole to the junction, and it is amazing because the Pacific plate is dead flat, almost like this floor in here. And then you come up to the North American plate and all this rubble goes up. And it's like the line between two continental plates is almost like the line at the edge of the floor here. It is really amazing how sharp a continental boundary is. I would have never guessed that until, or believed it until I really saw it down there. Yeah, so we have, Alvin has one window for the pilot up front. I mean, we can all take turns, and then the pilot looks out here, and each observer has a window down here. That's a window, and a window on the other side. Windows are these big acrylic prisms that sit in the titanium sphere in a hollow out, and they're just wide enough that you can put both your eyes in there, and you get a good depth perception. There's little lights outside, of course, that light, because otherwise you'd never see anything. Light is restricted to the upper 150 meters in the ocean, and which is where most of the biomass is. There's almost nothing in the rest of the water column, and then right at the bottom, you have the other about 4% of life down there, collecting all the raining particles down and living off of that. Other than hydrothermal vents, they get their own energy from the sulfide that comes out of there, combining it with oxygen. That's a whole other story that I won't go into right now. But Alvin itself, you sit in there, you look out, with little lights on the outside, and little tiny light bulbs that shine out, and that's how you basically get to observe things. But the pilot will be able to work with several mechanical arms that are out here, electric or hydraulic arms, and has a tool basket out here with all the tools that can take cores, take samples, bring things back. When we go out to the boreholes, we'll often have an electric connector. We'll connect to some of the data loggers that log pressure and temperature and tidal data and all sorts of things. And so there's a lot of things to do down there. When we go bring back a string, we will actually deploy a line with a milk crate on the bottom that has another line on it and a float on top. Alvin will go down, we'll go find that milk crate, grab the hook out of it, put the hook on our instrument string to there, do other stuff, come back, and then at night we'll go back to the float where that line is and pull up the whole line, and then with the full strength of a winch, we'll pull back the whole string of instruments that was in the borehole. And then we'll drop a new string down with a weight on the bottom so it sinks fast. We'll go down with Alvin the next day, release that weight so the whole thing is only 50 pounds overweight. We can then bring it over, drop it in the borehole, and then we'll cut off an extra flotation off the top so it sits heavily in the borehole and is good for another 5 years. And that's how we replace these instrument strings in these boreholes to continue our monitoring. So yeah, that was quite interesting. We did that quite a bit around. And then one of the things, the more recent things we did is we look at, we used the pH sensor, which was now the pH nitrate sensor. We got them small enough and low power enough that we were able to add them to what we call these apex floats. Apex floats are these really cool floats that have been used to study probably the first device that could really study the whole ocean basin-wide. We're not just looking at a coast, we're looking at the whole ocean basin-wide. And they've been deployed for about 20 years or so with only physical sensors, temperature and pressure and salinity. And those are the main things to look at water density, and that's how we learn really where all these deep water currents are going that all have different densities, and we could very well map the deep sea conveyor belt and of the deep ocean current. There were at that point, about 3,000 of them around there. The map on the lower left of the world, most of those black dots are where floats are currently. And so that you can see there's quite a few of them. Those are about $20,000 a float, and that's how many there are. They last about 5 years. And the way they work is kind of cool. They have a piston inside of them filled with oil, about 260 mils of oil, and inside a rigid housing. At the bottom, they have a flooded cowling down here, and that has a double bladder in it. And so by pushing oil from that piston inside the housing into that bladder on the outside of the housing, you're basically changing the overall volume without changing the weight. Therefore, you can control the density of the float. And since the deeper you go in the ocean, the denser it is, because that's how an ocean stratifies. The denser water is deeper, because it's colder down deep. And these floats are normally deployed. They sink down to, because they're all pre-programmed, they sink down to about 1,000 meters. They stayed about 1,000 meters for two reasons. One is there's not a lot of current down there, so they don't drift quite as far. And two, there's no biofouling down there, so we don't have the problems like we had, like you saw earlier on our moorings, where we get all these biofouling problems. And so then every couple of days, they suck in just a little bit more oil into their pistons, so they get a little denser. They slowly sink down to 2,000 meters. At 2,000 meters, they turn on all their sensors, start recording, and then push out oil, and then slowly do a profile in about 8 hours from 2,000 meters up to the surface. When they break the surface, they have the tallest thing on the left is a antenna, and it'll get a GPS fix, the first thing, get a GPS fix, and then it'll make, in the old days, it was a Argo satellite that you could just transmit to, and you hope you get the data. In all the new floats that we now have, they make an Iridium cell phone call, make a connection with their mothership on land somewhere, download all their data, upload any new instructions, and then go back down to 1,000 meters. And they can do this for a single float with lithium batteries, can do this for about 5 to 7 years. So it's at 7 years, they can't push, when the batteries get too weak, they can't push out the oil. And that's why we need sensors that can last that long and be stable that long and so forth. And that's what we worked on. So we had this great opportunity to take our new sensors and put them on here and basically bring the Argo program that only measured physical into what we call a BioArgo, or even often called, the BioArgo program that now has floats with a lot of the biogeochemical sensors, and that includes not just the nitrate and the nitrate and pH, but also we put oxygen sensors on there and transmissometer that, so it can look at backscatter and look at the number of particles in the water column, which gives us an idea of growth. We then got involved in a SOCOM project that was probably was a big bite to eat for us, because it was $25 million project between University of Washington, Princeton, and us, and we needed to deploy 50 of these floats per year in the Antarctic. And the reason was, in the Antarctic, the ocean is so much colder, so it's not as stratified. And the Antarctic, turns out, we learned from the physical floats about as we have climate change and the planet is warming, the atmosphere warms, the ocean, like around Hawaii, is very stratified and can't really absorb a lot of temperature. But in the Southern Ocean, where the ocean is open all the way around the circumpolar current, a lot of temperature can be absorbed and gets mixed, because A, the water is colder, but also because it's mixed a lot deeper. So it absorbed about 90% of the temperature that the ocean takes up is all taken up in the Antarctic waters, around Antarctica. So then the question became, great, if it takes up that much temperature, how much CO2 does it? And CO2 is totally different, a different bird than temperature, because it's biologically controlled, and so we wanted to really study how much CO2 is taken up by the Southern Ocean, because it could potentially have a big impact on the role of the ocean in climate change. So now, the last few years at work, I've been building about 40 to 50 of these every year, building, calibrating, quite an extensive procedure, and that's what I've now been able to pass on to somebody else. But we now have probably about 200 to 230 floats that have all these geochemical sensors on them in addition to all the physical sensors. And that's worked out really well. So if you want to look more, the SOCOM Princeton Air address has all sorts of information on those kind of floats and all the sensors on there. And it's pretty cool. As I said, one of the other last things here, or one of the projects I've been involved in, was these Osmo samplers, again, down in boreholes. In fact, MBARI decided that we had developed that, we got it out. The role of MBARI is really to develop instruments. So there was still a lot of people wanted to use these, to continue using these. So we asked for permission, and we basically, a friend of mine and I now run a little company that makes these for all sorts of projects, both for well testing on land as well as deep ocean testing. And one of the reasons I retired at the end of last year, because I had this great opportunity to go back to New Zealand and deploy some of the Osmo samplers that I've been spending the last 3 years designing, all after hours and at night, and in part with the University of Washington here in Seattle, with a colleague of mine up there. And so since I had that opportunity, I said, boy, I'd love to get back to New Zealand again, because I'd been there, always gone through New Zealand when we went to the Antarctic, and I had a chance to prepare, and all the osmotic pumps there, you see them filled with salt and so forth in a lab in Christchurch, and then we got all the coils ready. You might ask on the right, what are the copper coils for? Or that is a copper tubing rather than the Teflon tubing we use. And that is the copper tubing we use for sampling gases, because the gases, like methane, we cannot sample in Teflon because the gases will diffuse through. So gases like CO2 and methane we can collect in those copper tubings. It won't be clean for other ions, but it'll be for gases, they're fine, so we do gas analyses on those. There was a unique thing here. We actually had 4 ports we'd sample from, so we inject a dye in the middle from using the outflow of some of the pumps. We have a tracer that we inject in the middle, and then we have ports on 4 sides, and we can actually measure, we're trying to measure the flow of the rate of flow through the rock. And so by injecting the dye in the middle, if we see more tracer on the north side than we do on the south side, we know we have a south to north flow through the rock. So and we can then, through various modeling, we can actually look at what the flow rate is. And the flow rate, you're saying, what is the flow rate through a rock? Well, it actually does flow through rock, and through solid rock, it'll be on the order of millimeters a year. Where this borehole is, where we're doing is off of the red dots, off of New Zealand, where the Hikurangi fault is. The Hikurangi fault was the fault that slid when New Zealand had their big earthquake and Christchurch got damaged about 10 years ago. And we bored, actually in 2,500 meters, we bored another 800 meters, and I think about 400 to 500 meters below the surface, we installed, where the fault was, and we installed a sampler right there in that fault. And so I have another 5 years, and we're gonna have to go build another one of these, and we're gonna go back there and try and replace it, and we'll get that back. So it was a lot of fun. There's the drill ship in Timaru, getting just before where we got everything together. The whole sampler, this one was quite complicated, that's about 4 inches in diameter, and the whole thing was 65 feet long. And then once we got it all assembled, we had to raise it up in the drill tower and stand it up in the drill tower, and that was quite the operation. But once it was standing upright, it's fairly easy to put down in the hole once it gets done. In the top right, you'll see the racks and racks and racks of pipes that are all screwed together to actually reach the bottom of the ocean. The ship is actually capable of drilling in the seafloor up to 7,000 meters of water. But since we can't go back with submersibles to replace things, we normally don't go quite that deep. But that is our capability. So anyway, that's kind of where the things I've been involved in. So the second part of the talk, what I wanted thought I'd talk a little bit about is kind of the lesson learned from a career over here, maybe a non-traditional career where I kind of balanced science and engineering in a way. Lucky enough to be at an institute where I could do that fairly easily. And so what are the overall goals? I think most of us want to have a job that we enjoy, we have fun at, and we feel productive at. And so if I think back about my trajectory, it was really based on, again, the tools I had in my tool belt and the opportunities I had. I think looking at both my students as well as my 2 kids, I think my son Ben, who at 3 years old loved to draw, always had a pencil in one hand, paper in the other, knew at 3 he determined he was going to be a cartoonist. He went through school and is now in the film business in LA. There's very few people like that, I think, who really know what they want to do from day one. I think most people are more like my son Nico, who kind of knew he wanted to be by himself, but really didn't know how to apply what he wanted to do or how to do what he wanted to do, who went to college, changed majors a couple times, and ended up, actually for him, quitting school and starting his own business. Well, he started his own business in school, and that was more successful. And the head of the business school, where he switched from science to business, he met the head of the business school, who worked out with him in the gym every morning, who then told him, "You'll learn more running your business than you will I can teach you as a bachelor's in business." And he left school, and he's been now kind of figured out his way, and he's now in he does FBA stores fulfilled by Amazon, and has been traveling for 4 years, and he loves what he's doing and keeping all his costs low by, slowly living in $5 and $6 Airbnbs, starting out in Southeast Asia and then coming back home quickly, but then escaping again to Mexico, Central America, and a year in South America, and now in Africa, and having a great time. So it's also one of these totally non-traditional careers, but that are becoming more common. Over the years, I've had quite a few students come through our lab, and even there are definitely a few that stay in science, do our traditional science, but they're fewer and fewer. More people are having to find their own way, because all the science jobs the traditional science jobs just aren't out there as much anymore. So anyway, I've thought through basically about what I think is important for students to pay attention to. I have 4 kind of main lessons that I think are really significant, and 6 kind of more minor ones that I think are also important. First is, I guess, really stimulate and satisfy your own your natural curiosity. Don't just think about it, but go out, do things, take things apart. I took things apart, learned how they worked, and that is a way that I got into engineering. But it doesn't matter what your interest, it doesn't matter what I did, it matters what you do. Do what you love, go in and do it. Get interested in things, do the research about them, learn about them, and really do them. And I can't say enough about traveling, you know, especially traveling by yourself. You'll learn more traveling by yourself. I sent my kids to Europe the first time they were 16, and they went again when they were 18, and they came back as whole different people, and travel is definitely a real useful thing. Second is to really educate yourself. And I don't mean just educate yourself in school and universities. Yes, you will learn things there. You will learn the basics, you will learn your math, you will learn your science and so forth. But also continue working either at work through internships or apprentices, or even tools you have available at work. For me, for example, all the engineers at MBARI where I worked used a program called SolidWorks. It's a CAD program. And I never felt like I could really do it until one weekend I just said, okay, I gotta do it. And I spent like 3 weekends spending 16 hours a day going through all the tutorials. And that ended up becoming a really useful tool. Ever since then, I've done all my own shop drawings and sent things out to shops, and I've actually done a fair bit, learned my own machining on lathes and mills that really allows me to design things with what a machinist can do in mind. So I really encourage you again to actually do things. And most importantly, learn things on your own. Learn things, you know, just follow your interests, learn things on your own, and again, just add things to your tool belt. Be it a language, be it a creative, be it art, be it building out your bathroom or whatever. But if you do it, you'll learn so much more. And these skills that you learn doing one thing can be applied actually you'll find out, or I found out, can be applied in a lot of different areas. You know, taking apart that 3-speed hub when I was a kid proved really invaluable, you know, later on, learning those kinds of skills. Learn another language. My son right now is learning Chinese, learning Mandarin, because he says in 20 years, not knowing Mandarin will be like not knowing English today, or speaking only English in 20 years will be like only speaking Spanish today. It'll definitely will limit you. Third is find your strengths. Find what you like to do. And the reason this is really important is because doing what you want to do and what you like to do will make everything so much easier. It'll make you more productive. It'll make work more fun. And think outside the box too. Think about, you know, it's not just the job you're in. You're looking at a career. There's a lot of opportunity out there if you go find it. So be creative. In fact, a lot of scientists are quite creative. The best scientists are they're musicians on the side, or they're artists on the side. Being creative, thinking outside the box is quite important. And the fourth of I think my big lessons is opportunities. Opportunities in life is you really have to look for them. You can work to create them and take advantage of them. I mean, just a little letter I wrote to the woman who worked in the Antarctic was really creating that opportunity that came back and became an opportunity that I was able to take advantage of. It can be quite little things. My son in the film industry, got a job first wanted to because he actively pursued him, worked for him for free for a little bit, got appreciated, and now he's working full time with him. And so it's making opportunities, finding them, and taking advantage of them. That is kind of the heart of, I think, a lot of where a career can go. And a couple other things is trust yourself. I think a lot of students in today's world are told, you know, they got to do better here, do better there, but have trust in yourself. I think that's really important. Know what you know what you don't know, and build some self-confidence and esteem, and really trust yourself. That's really important. And the other is not to be afraid to be an entrepreneur. I think, think about starting your own business. It does work. It's a lot of people do it, but you can do it in academia or in science or engineering as well. Don't be afraid to try new things. Don't be afraid to take some risks. Yes, you want to be a calculated risk. If you start a business, yes, you want to write a business plan and so forth. Do something. If you want to design something, you can do the math calculations for it, but take a risk. It's okay. You can and start a business. And if you fail, you can definitely try again. But you always learn something from every one. Don't be afraid. And probably one of the more important things is to build friendships. I think building friendships, both personal, at work with colleagues, and also as a mentor. Find people that you would like, that are be good mentors, that can help you in your career, and also be a mentor. You can be a mentor too, and that's important. This is a picture here of David and me when 30 years ago, when we got to know each other. Our 4 kids here that were pulling along on a kind of a crazy invention trap we did here. We rode all over Monterey there. That was a lot of fun. But those friendships, they're important because they too lead to opportunities. Cultivating friendships lead to great opportunities. Time. I think life is limited, and time is worthwhile. Use it wisely. 5 years ago, I was diagnosed with cancer. I managed to beat it, at least so far, but it really gets you to think about living in the present, taking advantage of the time now. Don't waste time. And have a plan. Have a plan with your time goal. Try not to waste it. Be productive in your time. And last, I see a lot of scientists who've done their whole careers, and they really all of a sudden realize they can't retire because they haven't thought about finances. So early on, this is kind of a side, but develop a budget, stick with it, plan for the future, and really resist consumerism. You don't need a fancy car. A plain car will do fine unless you can really afford it. And probably last are be independent. And I think being independent, not being totally dependent upon one job, be independent, be ready to move if you have to, have a plan B, but being independent is probably a real hard thing to be for young students when you think about it, but it's a good thing to really not be dependent on a single employer or single other source. So that's an important thing. So lastly, I want to get back to your tool belt. As you go through life, you'll be adding tools to your tool belt. Think about the tools. Think about the tools that you already have, and think about the tools you want that will be useful to you. See again, what are your interests, but add new tools as you think would be beneficial and that really interest you. And use those tools. Use the tools because if you can use those tools, they'll excite you and they'll motivate you to work and will make work a lot more fun than if you have to do things you really don't want to do. Of course, every job has its non-fun parts, but that's okay. As long as most of it is fun, the more that's fun, then the better. And always continue to add tools. I think somebody once said, a day where you don't learn anything is a day wasted. And in that sense, always learning tools. Even later on, you will always be learning tools all the way through life. The world changes, you have to add your tools. And then lastly, in terms of like being independent and self-confidence, own your tools, be confident, they really are your tools. And then again, why was this called? Why did I call this talk Brains and Thumbs and Probability and Possibility? Well, you should definitely use your brain. We've been given those, but also do things. You learn a lot more by doing them. Ben Franklin said, tell me and I forget, teach me and I remember, involve me and I learn, and I'll add, if you do it yourself, you can also teach it. And that's why I say use your thumbs. Use your brain, but also use your thumbs. We have opposable thumbs. They're the best tool we have. Use them. And probability and possibility is kind of for a lot of projects that you work on, you want to do the calculations, you want to do the math behind it to make sure you can do the best research on it, but also use your imagination. Think outside the box. That's the way, that's the best way to move forward in any kind of research, is really to use your imagination and think what's possible and think beyond what others have thought. So that's among the best ways that I've learned to really kind of make. So kind of in conclusions, here I kind of try to summarize them, everything I've said. Learn about and do things that interest you by using both your brain and thumbs. Educate yourself, both in school, but probably more importantly, even outside of school. Find your strengths. You're most efficient at doing what you love, and take advantage of opportunities. Go find them, seize them, and I always say the best jobs that you can get are never advertised. I don't think I've ever had a job that was advertised. That is really the best, I think, the best way of finding jobs and finding opportunities. Again, cultivate your relationships on all levels, personal, professional, and mentors. And it is investing in these relationships that I think will create the best and most unique opportunities. And so that is really worthwhile to do. Be confident and independent, use your tools, and last, and I think, is follow your instincts. Listen to yourself as you learn from others, but listen to yourself, and it is your own instinct will tell you often, will be a really good guide in where to go. So last, I don't know why, but oceanographers always end with a sunset, and so this was a picture I took down the coast from us, and with that, I'll be happy to take questions.